Good morning, everybody. Today we are going to talk about how to efficiently store data in your cloud environment. Well, we can probably all agree that cloud should be all about efficiency. And if we talk about efficiency, we need to think about the biggest static cost that we have in cloud, and that is the data. You can't avoid not paying for storing data, because for every gigabyte of data you're going to have a certain price, and those gigabytes can add up to terabytes, potentially petabytes, zettabytes, exabytes, right? The idea that you need to have in your mind is, how do I efficiently store my data? Now, there are two types of data that generally need to be stored in any environment, and that is going to be your online data or any kind of data that needs to be accessible immediately or within seconds or potentially within minutes. And then your offline data is going to be any kind of data that you need to retain due to compliance, governance, due to any principles that you have to follow when you do business. That's just the fact of life, right? How do we treat data on premises? Well, first we've got a production storage, right? Some kind of block storage environment. There could be many of those, but some kind of centralized block storage environment, usually kind of high performance SAN environments where we run things like databases and our BI and our ERPs and all of our other kinds of software that requires fast, efficient block storage. Now, on top of those, what we can do is we can add something like file storage. And file storage, usually you're going to have a cheaper solution because you're not going to need that much performance. So besides that high performance SAN, you usually have some kind of lower performance SAN or NAS device, so network attached storage device, which gives you the ability to build shared file systems. Then you have your block storage that's attached directly to your servers, where you run your operating systems, where you run your hypervisors, and then do things like cache and accelerate your environments with locally attached SSDs, etc. Now, those are all online type of storages that you can find inside of your environment. Maybe you'll have some kind of disk-based backup. Disk-based backup is somewhere in between online and offline. It's super quickly accessible, so you can restore really quickly. You have also something like, let's say, shadow copies on Windows file shares, where you got a copy of the file that's sitting there on the file system that can be restored. So those two can play a similar purpose. And then finally, you'll have something like a tape-based backup. And a tape-based backup will ensure that you can retain data, and you can retain backups, and you can retain copies, probably multiple copies of your data, for a very, very, very long time. And why am I saying multiple copies on tape? Well, you'll have, let's say, a server backed up daily or weekly to tape, and that will be like, lots of times all that data is replicated. Lots of time it's a full copy of that content, and sometimes you can do incremental copies, which can save you a lot of space. However, if anything breaks in the incremental chain, you can lose your data, right? So lots of times we do full backups, let's say full backups on the weekend, and then incremental across the week. This will be dictated by our recovery policies, right? What we need to recover, how we need to recover. Lots of times, for simplicity's sake and for consistency's sake, a full backup is done just because there is no potential problem that can happen because of an incremental backup. And that's because the tape storage media does corrupt, right? The tape storage media does have a limited lifespan, and that limited lifespan and those potential corruption issues just won't be detected until that data is needed at some point in time, right? Until an audit comes along and says, show me the data from 3 years ago, and then you restore that data from 3 years ago, and you discover there's, multiple 1-bit errors on that tape, and because there's multiple 1-bit errors on that tape, you can't recover that data. Now, of course, lots of you will say, well, yeah, that's why you use error checking and correction. That's why you use all of these, advanced corruption prevention mechanisms, like, calculating parity for your data and also storing parity for your data. But again, it's besides the point. The reliability of the tapes could, influence everything. It could influence your data. It could corrupt your ECC checksums, right? So eventually you're gonna need like multiple copies of data just to ensure that your tape survives. And this is where the biggest sort of challenge is in traditional data centers. It's the tape storage that just needs to exist because of compliance, because of governance, because of laws and regulations sometimes. Now, when you move to the cloud, there's no more tape. There are services. And if we take, for example, AWS, where I probably do most of my work and where I'm most versed in these storage solutions, I'm going to compare our storage solutions in the data center to storage solutions in the cloud. So the big benefit of cloud is everything is disk-based. Everything has very high durability, right? So when we talk about persistent storage, most of your data should reside on S3 if it's online, and then the rest of it should reside in Glacier if it's offline. Glacier is akin to tape storage. It's offline. It's not always available. You have to issue a restore, and then it takes time to restore that data. However, Glacier is all disk-based and has the same durability as S3. So we're talking about 11 nines of durability. And 11 nines of durability, you will find this durability across pretty much any cloud environment. It's essentially the theoretical calculation of when things can go wrong. So think about what 11 nines means. It's at least 3 copies of data on 3 disk drives in 3 different data centers in 3 different servers. Now, for you to lose a file, you need to corrupt 2 of those files in the same spot, right? 1-bit errors do happen on disk. They are recoverable. 2-bit errors do happen on disk. Sometimes they're recoverable, sometimes they're not. In most cases, they're not, right? So what you need is a 2-bit error happening in 2 disks, in 2 data centers, on 2 servers, in the same spot to corrupt that one file. The actual statistical probability of that happening is 1 in a million across every 10,000 years. And that's your 11 nines of durability. That's 99.99999% of durability. Is you can expect to lose or corrupt 1 file out of every million files that you store every 10,000 years. And that means that the possibility of corruption is so low during the time that you're storing that it's virtually fully reliable. Virtually fully reliable. You could be, it could be bad luck, and it's like year number 1 that happens to you. But typically, we'll store data for way less than 10,000 years inside of our archives. Usually, it's 5 years, maybe 10 years. Sometimes, talk to government agencies that have to store data for 15 or 20 years because they are mandated by law, by actual law. They will break a law if they do not store that for that amount of time. Another benefit of something like Glacier is when you store data, you always append. You do an infinite incremental process. Because of that high durability, you don't need to worry about that data being corrupted. And even if you do stop and do a full backup, the cost of storage is very, very low. So for example, Glacier Deep Archive goes to $1 per terabyte per month. Per terabyte per month, right? So think about, let's say, how much does a 10 terabyte disk cost? About $300 off the shelf, right? So that's $30 per terabyte. So basically you have 30 months of storage for the price of just an off-the-shelf disk, not including the power, not including everything else, which is a pretty good price, because you're not going to be storing that data for longer than that amount of time anyway, right? And of course, as the price of disk goes down, Glacier Deep Archive will get bigger disks, and those bigger disks will then, of course, potentially eventually reduce the price of Glacier Deep Archive even further down than what it is today. That's happened with S3. S3 is now basically cheaper than the S3 reduced redundancy. So reduced redundancy is not even recommended anymore for anything. It's basically only where things like Glacier restores happen. That's the only time that you use reduced redundancy in reality. Yeah, so what we need to think about is, okay, we got our storage covered. Now we want to do online storage, right? So if your application requires the data within minutes, online data within a maximum amount of minutes, maximum amount is like maybe 5 minutes after I issue the request, I need to get that data, right? You can have terabytes and terabytes of data stored on S3 because the price is really good, right? The price of S3 is, list price is like 2.3 cents per gigabyte. Again, it depends on the region where you're at, but if North American prices are like the standard that I'm sort of basing all of this on, it's 2.3 cents per gigabyte per month, right? So basically we're talking about storing a terabyte in an online format where it's immediately accessible for what would that be? That would be about $20 a month, right? That's a terabyte of data. So that's a pretty good price. Why do we want to keep that data in S3? Well, if it doesn't need like millisecond latencies, then keep it in S3. Then going further, you're going to have some data where it would be inefficient to do querying on S3, right? You can query data on S3, you can query just S3 directly and do, some querying of files internally if they're properly formatted. Or for some formats, you can use something like Athena, which is a online query engine that loads the data from S3 into memory, and then you can run SQL queries, ANSI SQL standard queries against that data. So for example, if you have something like a CSV file where it's a table, or if you have a Parquet file where it's already a columnar database format, or if you have something like a text file with some kind of structure in it, some kind of structure where you can apply some kind of regular expression to structure that data, then you can run Athena and query straight off of S3. This can be really efficient, but Athena has a price where every terabyte of data scanned costs $5, right? So if you're scanning a lot of data every day, then maybe it makes more sense to put it in a database and pay per hour for that database service. So here is where something like Redshift comes in. Redshift is a petabyte scale data warehouse. With the newest RA3 nodes, you can store up to 8 petabytes of data in the cluster with 128 nodes. So that's a huge capacity, and we're talking about one table of 8 petabytes, and we're talking about raw storage, not actual compressed sizes, because Redshift internally compresses everything in that columnar format that it has, so that 8 petabytes of storage actually can store like 20, 30, even 40 petabytes of actual data in there. So that is something that's really beneficial with of course with Redshift. So when we look at Redshift is great for like large analytical queries, or you do large scans, and replaces Athena when these scans are very often, when it's large data sets that are scanned and queried very often. Now if you have small data sets where you need fast responses, where you need like millisecond response times, then of course a traditional database like something, like MySQL or Postgres or even Oracle or Microsoft SQL works. You've got the RDS service that does that for you. Or you can go for Aurora, which is like a next generation database. I've talked a little bit about databases. I'm going to give a link in the description to the databases, how to select the database. And what you want to have is you want to have only the data that you really query in that database, right? Only the really like latest data. And then again, you need to figure out what that data size is and then lifecycle the data from your database into Redshift, and then from Redshift into S3, and then from S3 into Glacier. Now, if you need like microsecond performance, then on top of the database, you can also add a caching layer, right? You could have something built with Elasticache, like a memcached or a Redis cluster, right? And that will give you extreme performance. That will, go reduce your latencies down to microsecond for most responses that are cached. You can do the same with DynamoDB, right? You can use DynamoDB instead of a relational database if you have key value stores. And as I've shown in one of my previous videos, now you can use Particle on DynamoDB, so you can write your traditional select, insert, update, and delete statements, which is super cool, right? So we can now use a very fast millisecond latency database for all our database traffic to basically scale to infinity, essentially, right? You have infinite scale with DynamoDB, and that's the beauty of DynamoDB. Infinite scale and super fast, consistent performance at all times. So here you can replace your traditional database also with DynamoDB. You can add caching in front. You've got DAX, which is the DynamoDB accelerator. That can again bring down the latencies down to microseconds for reads. So what you need to configure is just how much data do I need in the fastest environment, how much data do I need in the second fastest and the third fastest, etc. So typically when we build a full life cycle of data, we look at, okay, our relational database or maybe our DynamoDB is going to be our core, where we determined how much data do we actually need online. And typically it's something like, let's say, a week's worth of data or a month's worth of data needs to reside in that database, right? Because we are working with current month or current week, depending on what the life cycle of the business is, right? Then we look at how much of that data is read, right? Let's say if 80% of that data is read, 80% of the operations are read operations, then what I can do is I can push that commonly read hot data into a caching cluster, a DAX or Elasticache cluster, doesn't matter what we have, and we can scale the caching cluster to support as many of those reads as possible, right? To capture as much of the cache data as possible. And then further down on the back end, we say, okay, then after a month, let's say, we'll life cycle the data into Redshift, right? So Redshift is great because, for example, with DynamoDB, it supports direct copy operations off of DynamoDB. What is a direct copy operation? Well, any table that is in DynamoDB, you can just issue a copy operation off of Redshift, and it will siphon the data off of Redshift and drop it, siphon the data off of DynamoDB and drop it into Redshift, which is a really, really cool operation. And it makes lifecycling data into the data warehouse really, really easy. So how much data do you need in your data warehouse? Well, to do good, let's say forecasting for the current year, a year's worth of data is typically what you have in Redshift, maybe 2 years worth of data, because you want to keep last year's data quickly accessible and do comparisons. Again, this highly depends on your business process, right? Once you're done with Redshift, you can lifecycle data out to S3, and lots of times what we do for that second or third or fourth year, we leave the data on S3 and then address that data with Redshift Spectrum whenever it's needed. So Redshift Spectrum is also a query feature of Redshift, where essentially it's like Athena, where some ephemeral capacity is available to query data that's sitting on S3. Now, in the case of Redshift Spectrum, it's actually adding ephemeral resources to your Redshift cluster, loading the data from S3 onto that Redshift cluster, and then querying the data that's on S3 and the data that's in your cluster together. You have the ability to query both, do joins of tables that exist inside of your cluster and inside of the S3 environment. And this is where Redshift Spectrum really makes sense. If your data warehouse is Redshift and you want to store data in a cheaper manner, you just lifecycle older data that is not queried frequently into S3, and then you have the same price for queries. It's $5 per terabyte of data scanned every time you issue a Redshift Spectrum request. And there is no Redshift Spectrum as a service. It's just an extension of your Redshift cluster. As soon as you point to an external table, scan that external table, then you're using Redshift Spectrum, right? It's literally the same SQL interface of your Redshift cluster. All you need to do is define an external table and then query it, and then boom, you're using Redshift Spectrum. And then of course, some of that data that's sitting on S3 might even not be something that used to be in a database, right? Some of that data might be static files. Some of that data might be a file system kind of type of data, right? I've already mentioned in one of my previous videos that you can now use S3 as your file system because it's read after write consistent for all operations, including metadata operations, which means that it is now essentially no different than a file system, with the benefit of having 11 nines of durability, with the benefit of having 4 nines of high availability. And this is going to be a game changer with applications that are now depending on a file system, just because you need that file system to be read after write consistent, not because you're opening files from multiple places, right? The traditional file system, when you open a file, it still resides on the file system, whereas with S3 you need to bring it locally and then you'll open it and manipulate it locally. So there still is a difference, but lots of times it's just manipulating the file and storing it locally and then uploading a new version of it. And S3 also supports versioning in the back end. So that's the idea. And then after, like, for example, you have your 3 years of data stored on S3, all older data you can lifecycle into Glacier and have, let's say, the last 10 years, minus the 3 years that you have on S3, pushed into Glacier for retention, for compliance. If you need to pull it because of an audit, because of something, you then pull it out of that storage. So basically, look at it like this: 70% of your data is going to be in the cheapest storage, it's going to be in Glacier. Then an additional maybe 20% is going to be inside of S3. Then another 9% is going to reside on Redshift. Then another 0.9% is going to reside in a database, in a transactional database, and then 0.01% or 0.1%, yeah, is going to reside in your cache, right? And cache is most expensive, then your relational database or DynamoDB is cheaper, and then Redshift is cheaper, and then S3 is cheaper, and then Glacier is the cheapest solution. And you're going to store most of your data in your cheapest solution. And that's where you should be at. That's how you should be thinking about storing your data inside of cloud, inside of AWS, inside of Google Cloud, inside of all cloud solutions. It's all about making sure you lifecycle data as soon as it's feasible to do so into the cheapest solution. All right, that is going to be everything about this one. So thank you very much for watching. And if you like this content, I would like you to subscribe. This would mean a lot to me. 98% of you are not subscribers. So yeah, push a like and a subscribe, and I'll be really happy. Thank you very much. Bye.